back with this last lecture.
Okay. Good morning, everyone. Thanks for making it this early morning final day. Today I want to kind of put the things that I talked about in the previous two lectures together. In this first lecture, I hopefully somewhat convince you that these tensor methods, they are useful. I didn't really show you how they work variationally, but I try to convince you that these things are useful when you're interested in the low energy physics of Hamiltonian, because ground states of local components satisfy an area law, and these tensor networks exactly target those states that satisfy an area law. So they are a good variational approximation to ground states of local cap Hamiltonians. In the second lecture, we talked a bit about these matrix product operator symmetries, and I will sort of come back to this a little bit. This was much more mathematical. We used the ideas of module categories, bi-module categories. Today we will also talk about module functors. So this is quite sort of mathematical set of ideas that describe these symmetries in these models. And in this final lecture, I'm going to try to throw those two things together and argue that by looking at these symmetries from this very abstract categorical point of view, you can nevertheless translate all these ideas down to what at the end will become better ways of finding these matrix product operators, matrix product state, ground state in practice using variational algorithms. So using these ideas, we'll actually be able to exploit the structure that's present in some of these matrix product states and find them more efficiently. That's kind of what I'm trying to build towards today. Okay, so last time we ended basically on this set of pictures, so I will go through it again because I realized I went rather quickly. So what we were talking about or trying to figure out is I have some tensors here, these white tensors here, which I told you, okay, they make up the wave function of some 2 plus 1D state. And I said that if I want this state to have some interesting properties, namely, if I wanted to have topological order, then it needs to have these matrix product operator symmetries. So that's these red lines that I can push through freely. So last time, just by looking at the fact that these matrix product operators have to form some closed fusion ring, we were able to derive all these kinds of properties on the various tensors that enter into well, you can define these kind of fusion tensors here that will implement the product of these matrix product operators locally. And then those fusion tensors, they have to satisfy some associativity condition that comes with an F symbol that has to satisfy a pentagrammatic equation. So just from starting from these matrix product operator algebras and requiring them to form a closed algebra, irrespective of the system size, you end up with having to study fusion categories. So this is how we fell into this. We didn't start out wanting to do fusion categories. In fact, we would have preferred not to. It just sort of comes out very naturally if you start thinking about these topological symmetries. Okay. And then so these 4 equations are what I talked about last time. And then I said, okay, just looking at this equation and trying to solve it by brute force is very hard. I have a very complicated polynomial equation. If you're given a generic tensor of this form, it's actually pretty hard to find these matrix product operator symmetries. And so that was sort of the situation, I think, 10 years ago when Frank and collaborators started looking into this, and then out of pure misery, basically, they figured, okay, let's actually try to find some exact solutions. So I tried to go somewhere, try to find some kind of special states where we can have this property exactly. And then you end up with these models for topological order, like the 11-1 model. And if you try to if you write down the tensor network ground states for the 11-1 model, which is easy to do because it's a commuting projector Hamiltonian. Any commuting projector Hamiltonian has a very straightforward tensor network representation. You find tensors of that form, which we derived last lecture very quickly, and you find that these indeed have these matrix product operators. So last time, yes.
Just to understand, make sure I know the notation.
Yeah.
Your red lines are the fusion category, and these white lines are the module category.
So the red lines are this fusion category C.
Okay.
The white lines are another fusion category D. They are connected by an invertible bimodule category, and I will be using this notation for an invertible bimodule category. So then this bimodule category itself is blue. And so these blue lines, they don't show up in these pictures here because they label the auxiliary degrees of freedom. They are the entanglement, the virtual degrees of freedom of these tensors that build up this topological state. But they also constitute the space, virtual space of this matrix.
Okay. So I should think of each diagram as an object of the fusion category, right?
Right. So here I should be writing x. So x is some object in the fusion category, and then I also should be writing y1, y2, y3. And then similarly here I should be writing x1, x2, x3. And this is y.
Oh, sorry, but where, could you say again where I should think of the bimodule categories as being in this picture?
So in this picture, it's sort of hidden. These pictures are basically, that's what I was going to get to, but I told you that solutions to this equations, or at least a set of solutions to this whole set of equations, is obtained by defining some invertible bimodule category between some fusion category C and a fusion category D. That invertible bimodule category comes with a whole bunch of data, a whole bunch of associators.
Right.
Part of those associators are this one and this one. These are just the associators of C and of D and C.
Right.
And then you have all these module associators and this bimodule associator here that allow you to define explicit tensors in such a way that these equations will be satisfied. So if I do that explicitly, what you can see is that, okay, let's do this one here. So if you fill out these symbols here, and I'm going to be very schematic, right? I'm not keeping track of all these indices just because it's very annoying, but you can do it. If you look at this equation, what this schematically looks like is this bimodule associator times this module associator here is some sum over, on the right hand side here, you find this module associator and then twice this bimodule associator, for instance. So this, if you plug in these things to this equation here, you find this equation. This is one of the pentagon equations for the bimodule category. That's going to be true for all of these other ones as well. So let me look at this one. This is sum over f of this. This is another pentagon equation for the bimodule.
I think I understand what you're saying there, but it's just, so this bimodule category should be thought of as an interface between
Exactly.
those things, right?
Yeah.
So, but how are you thinking about the interface? Is it where the
It's a little bit hidden. It's a little bit hidden indeed. So
yeah.
traditionally, you would like to think of this bimodule category as an interface.
Right.
You should think of this bimodule category here as an interface between this fusion category that labels these white lines and this fusion category that labels these red lines.
So, but diagrammatically, are you
Diagrammatically,
thinking
it doesn't
about
quite show up as an interface in this case.
Okay, that's right.
That's sort of, we were confused about this for a while too. When we were reading Young's paper, he was talking about interfaces. And, so for now, there is a way of understanding this as an interface, but it's a little bit complicated. I don't want to get into it. Really, all we need is that you have this.
It's just that I can't understand how the diagrams express this in equation without seeing the interface.
Yes.
But
Yeah.
anyway, that's fine.
Yeah.
Could we on one of these do a little index count, like how?
Yeah, good. So, which one do you want?
The one with the little bow tie.
Okay, good. So, I would write M1, but let me use R. R1, R2, R3, R4.
And this lives in R, right?
Yes, in this module category. This is Y, which lives in this guy, and then X. So that's 6 integers, which makes sense. And then there's multiplicity spaces, I, J, K, L. These are vectors in the relevant home spaces on which this F symbol acts.
So if I want to translate such a diagram into an equation, I just chop it off.
Yep.
And then I have all these building blocks, and each of these becomes a. And then so first I add the blue circles.
Yeah.
And then I label each blue circle by a consistent symbol, and then I chop.
Exactly. Yeah. And these are really just Bachmann moves. All of these are just Bachmann moves. They are. All these things are tetrahedra, right? This is a tetrahedron. This is a slightly strange projection of a tetrahedron. This is another tetrahedron. You're gluing these things together, and then these equations are nothing but the Bachmann. But for those of you that are familiar with states and TTFTs for 3D TTFTs. Okay, and then I can do these final guys as well. So that would be something like this. This times this bow tie F is sum over bow tie F tie F. Triangle F, that's another pentagon. And this guy here is F is sum over F tilde. So at this point, what we are using this invertible bimodular category for is really just to find solutions to this equation. Right? There's a question of why do you take invertible bimodular categories? Any bimodular category would give you solutions to these equations. This has to do with wanting these two guys to be Morita equivalent. So you need some additional consistency property if you want the symmetries of this topological state to really capture the excitation content of that topological phase as well. So, yes?
Sorry, can you explain the label again for because in the horizontal one in the middle, on the left you label I and on the X. Oh, X is here. Okay.
And then I should have written the Y. And then these guys here. So anytime three of these lines meet, there's a vector space sitting there, the home space of. Well, in this case, it's all home space.
IDLK is the
vector in that home space.
Yeah.
Exactly. Yeah. I need these to be numbers at the end of the day, right? Because these are some tensors. So these are the components of some tensors, and I'm contracting them in a way so that it's an equation of it.
Perhaps with the bow tie, how many indices would it depend on? So
Then,
they're also 10.
yeah.
Is there also how many on the left? Because there are also indices on the left side.
Here you mean, or here?
Well, don't you, I mean, to fully make an index equation, you need indices on the left as well.
Right. So I'm sort of saying this tensor here, which has this is just using the ordinary tensor network notation, right? I have some vector space here, some vector space here, here, and here.
I can represent it as
Right.
in terms of cubic couplings.
Exactly. So what I'm doing here is I'm fixing these lines here, and I'm saying, okay, this is to make it precise. I would have to take direct sum over all these module labels here.
Okay, so you don't need extra indices, so you only need those.
So these two additions if you like. Fixed.
Just x and y. So it's
Yeah.
x, y, then 4 of ijkl, 4 of r's.
R's. Yeah.
So it's
That's all direct summing over all these indices that are not appearing on the left hand side.
so it's an index structure.
Exactly, and it's the same here. So here it's y1, y2, y3, y1, y2, y3. But then you direct sum over everything that's not labeled, and the same for the. So this gives you a set of yes.
So in principle, you could also have maybe different bimodule categories and bimodule functors between them and natural bimodule natural transformations. Is this simply not needed in this framework?
We will use module factors in just a bit.
Okay.
Yeah.
If D&D are fusion categories, what is R?
R is a bimodule category set connects them to. So a few things that are going to be important. Again, I'm imposing this to be an invertible bimodule category, which is I want some additional properties of these things that I'm going to go into. If you fix a fusion category C and a module category R, the fusion category D, for which this thing can be made into an invertible bimodule category, is unique. So, where should I put that? Put it here in this little box. So, either you think of fixing C and R, in which case D is going to be given as the category of C module functors from R to itself. Or the other way around, you could say C is given by the category of D module and functors from R. So either this means something to you, in which case, great. If this doesn't mean anything to you, just take it to mean that given a C and an R, I can compute what D is. So one classic example of an invertible bimodule category would be the case where C is, let me write it here, C is vec G, the category of G-graded vector spaces. D is rep G, the category of representations of that group. And then this R here is just the category of vector spaces. So what I mean by this equation here, that given a C and a modular category, this guy is fixed, is because basically, well, if you're given a group and you're given the kind of objects on which it acts, which in this case is just a category of vector spaces, you will automatically get the category of its representations. And vice versa, if you know the representations of a group, you can read off what the group is. That's just to give some intuition into how these kind of things work. It gets a bit more intricate for general categories, but it's basically the same kind of idea. And then the fact that you have some notion of an invertible bimodule category basically becomes some kind of sure orthogonality conditions on the characters that we get for them.
So vector G is G-graded vector spaces.
Yes. It's just a way of defining a monoidal category with objects that fuse like a group. It's kind of a fancy name for what in physics we would just call a group.
So this is here is an assumption that you're putting?
This?
Yeah.
No, this is true for any invertible bimodule category.
Oh.
So I'm saying that if I give you a C and an R, and I require this thing to be an invertible bimodule category, then D is going to be fixed to be this, or vice versa. And this kind of being fixed is something that we will use later. Maybe one. Sorry.
Can you repeat your comments about this show wild duality?
I can explain it in more detail maybe afterwards if you want. It's a bit involved. It's basically some requirement on this bow tie F here. There's an additional equation I could write down that it has to satisfy for it to be invertible. So mathematicians know what it means for this thing to be an invertible bimodal category, but we're not mathematicians, and we think about these fusion categories just purely at the level of these F symbols. So we wanted a condition at the levels of these F symbols that tells you, okay, this thing is invertible, this thing is non-invertible. And we came up with something that's basically sort of a sure orthogonality condition. It has to do with the character theory for these things are representation categories of some weak Hopf algebra, and it's basically some orthogonality of the characters of that weak Hopf algebra. Something like that. It's not complicated, and I think it was known in the literature, but it was nice for us to spell it out. I think.
So at the very beginning, you said that the level model, you consider the ground state level model equal expressed in terms of tensor network.
Yes.
Yeah, like G ground state. But here, but that one only involved one fusion category.
Yeah, that one involved this
Right.
guy here.
Then what is the meaning of this type of tensor network?
So these are all different. These are all distinct tensor network representations of the level-one ground state. So I'm telling you that there's a choice. If you want to represent the level-one ground state using tensor networks, there is a choice determined by a choice of module category R over this thing. And you can choose whichever one you want.
You mean they represent the same phase? They're not the same ground state, but
They might be. So on the sphere, they're all the same ground state because there's only one. On the torus, generically these things will represent different ground states. I will give a very quick sketch of how you can see that they are. But locally, these things are equivalent actually, because we will see that there is actually an operator that allows you to change this module category, which is going to be this module vector, which allows you to locally relate these tensor network representations. However, globally, you might end up with a different ground state.
I remember in the previous lecture, you mentioned that you can start from the one model ground state by applying finite circuit. That's the
Yeah, exactly. It's a choice of circuit, basically. So you can go from any 11-1 ground state based on some fusion category to any other 11-1 ground state based on a Morita equivalent fusion category, because they're in the same phase, with a constant depth circuit. And that's the thing that will relate these different. Okay, one final thing I want to say about this is that if you just write down this set of equations, these invertible bimodal categories are not the only solutions to them. They're a bit more constrained. They assume a little bit too much. If you just completely generally look at what do I need to define a consistent MPO algebra, and you don't assume anything other than that, you end up with the fact that these things have to be representations of bi-algebras. So you just need a product and a coproduct and nothing else. And in general, these MPOs can capture that. It's just that if you assume then all these other properties, which turn these things into an invertible bimodal category, you get a bit more flexibility. You can move that around however you like. You have a unit. It's closed under the dagger, all these kinds of properties, but you don't have to assume any of that. So there is a sort of more general version of these things, which has less properties, but can capture some symmetries that you could not capture just using these kind of language.
So can I try and say that with the word fusion category? So that means you have a sort of a modification of fusion category where you have a tensor product that's semi-simple, but you don't assume tensor unit and you don't assume duals.
Exactly. So it's really like the minimal thing. The only thing you get is an associative, basically, and nothing other than that. And that's what you get if you look at the representation category of a generic bi-algebra, even pre-bi-algebra, we call it, because it doesn't necessarily have a unit, and sometimes people assume it. These things here would arise as the representation categories of weak Hopf algebras, which have a whole other list of properties that you don't necessarily need if you're just looking at symmetries. You do need them if you want these symmetries to be topological, I think people would say. If you want to be able to bend them around, you need things like antipode and blah, 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 all this kind of stuff. But we're going to be looking at these things in the context of symmetries of Hamiltonians, in which case you don't actually need those. So that's the next thing. Okay. Let me do a quick look here. So this was sort of a recap and maybe a bit more detail of what we did last time. So I want to talk now about symmetric Hamiltonians and dualities. So we said I'm going to be interested in writing down Hamiltonians that commute with these symmetries. So now, this was all talking about 2 plus 1D states. I'm now going to be talking about 1 plus 1D Hamiltonians, so Hamiltonians on a line. So I'm going to be assuming that this Hamiltonian is some sum of local terms. And I want these Hamiltonians to have some symmetry. Now, if you look at this equation here, you should see that this leg here is open, right? So this equation will hold regardless of what I contract this leg with, right? That's clear? So if I want to build a symmetric Hamiltonian, all I really have to do is take 2 of these guys. So this guy that's flipped is really just the dagger of this thing, and multiply it with some some matrix, in this case Gi, which will contain the couplings of this Hamiltonian, right? And so, because of this equation here, this Hamiltonian will commute with this symmetry. It's kind of clear. Gi is so I have this equation where, okay, let me call this. This is true for all x. So this equation here gives me a way to systematically write down Hamiltonians that commute with this symmetry. I took a nearest neighbor Hamiltonian that's just acting on two sides here. It really doesn't matter. I could have taken this however big I liked. It's exactly the same kind of
Sorry,
construction.
what do you, on the left side you have a sum on I, and then there, what do you?
This is like the interaction strength at site I. It's some couplings. Actually, this GI means more than just the couplings. It also determines the on-site Hilbert space, so which specific representations that you're choosing. It's like if you're doing an SU2 symmetric model, you could look at the spin 1/2 chain, spin 1 chain, spin 5 chain. That's all contained in this guy here. The only thing that's important is that the Hamiltonian, if it's a linear combination of these diagrams, it will commute with the symmetry. You can prove that any Hamiltonian of this kind can be expressed in this form. That's something that actually uses this sure orthogonality condition that I talked about before. I will not go into details.
Excuse me,
Yes?
what is the relevance of this vertical line right next to it?
This guy here?
No, to its right. Only a few centimeters.
This line.
Yes.
So that's this line here. So I have this line, this line, this line. Those are the lines on which this thing acts, and then there's this free leg here that I can do whatever I want with. Right? So this line, and this line is this line, this line, this line. And I'm saying, okay, I have this auxiliary line here that I can contract with whatever I want, and it will give me something that's. So you should think of this diagram as these two things fusing into this line and then splitting again into this line. But there's some home spaces sitting here, and those I just pick some vector in those home spaces. Doesn't matter which one.
Thank you.
It will commute with this. Yes.
In the first lecture, you wrote the Hamiltonian as some string of these three valent vertices.
Did I? That was a matrix. I think I was talking about the matrix product states then. That's a state. So here I'm talking about a local Hamiltonian. So this is something that really, okay, I'm sort of saying there's some tensor product, or there's some big Hilbert space on which this diagram acts. So really I should be drawing this Hamiltonian as a sum of diagrams like this, right? So this would be how the Hamiltonian acts on this Hilbert space. I'm just looking at this local term. So in physics, we usually omit writing all these identities because it's annoying. So we just define this Hamiltonian to act as the identity everywhere outside this. And then this is just some local interaction.
I see.
Oh, sorry.
Yeah.
What did you mean by the Ri? What is that?
R.
Or is that Ki? What sum over
This
the definition?
HI?
HI, okay.
Yeah, this is just saying this Hamiltonian is a sum of local terms, HI. And each of these HI looks like this.
Oh, I see, okay.
Where this GI are some.
So, and your notation is that HI is an object of DI? No, D? Your previous notation. Two fusion categories.
Oh, right, okay, so there's a Hilbert space living here, so this is some, I should say, probably, okay, this is then also some direct sum over labels Y, this is Y1, Y2, Y3, Y4, Y5, like that. So, okay, this GI here basically controls which objects am I choosing, so what is my Hilbert space composed of, what objects in D is my Hilbert space built from. In that case, this would be like saying, okay, I'm looking at spin 1/2, or I'm looking at spin 5, or I'm looking at some other representation that's maybe not irreducible representation, something like that. Plus also, what are the different couplings? Like, basically these things come together, they fuse into some spin, I give that some weight, that's all encoded in here, and I split it again. So this is just encoding a generic symmetric Hamiltonian, it has to be of this form. Really, this is just generalizing what you know about Hamiltonians that commute with some group symmetry. If I have some SU2 symmetric Hamiltonian, we know that it has to be built from Clebsch-Gordon coefficients. I'm just generalizing this here to these matrix product operator symmetries. So what I'm really saying is that these guys are the Clebsch-Gordon coefficients for these symmetries, and any symmetric Hamiltonian has to be built from linear combinations of those guys. So basically what I get from this is that, okay, H commutes with these operators O, X, O, X. So indeed, this gives me asymmetry. Now I want to say something about the spectrum of such a symmetric Hamiltonian and what the spectrum actually depends on, and what, more importantly, what it does not depend on. So, if you look at the algebra.
Sorry, do you mean the commutator equals 0?
The algebra of these local symmetric operators. So if I look at the algebra generated by these local terms hi. So what I mean by that is I'm looking at the identity, I'm looking at all the different hi. I'm looking at hi times hi plus 1, hi times hi plus 2, hi plus hi plus 1, hi, and so on. So I take all possible products. This is some infinite dimensional algebra if you have an infinite dimensional. If I'm looking at an infinite dimensional chain, this is some infinite dimensional algebra. This is something that we call the bond algebra. So it's the algebra generated by the interactions in the local terms in your Hamiltonian, which okay, for some reason bond algebra, you didn't invent this name. What you can do is you can try to define an orthonormal basis for this bond algebra. So let me call that Bi. Let me say this algebra is called A. This algebra A is the span of these elements B, let me call it Bx. In this basis, you can write Bx times By is the sum over Z of f x y z of bz, right? These are the structure constants of this algebra, right? So I'm just going to this basis because it's easier in this basis to talk about the structure constants, but okay, this is really just following from well, the fact that this is a closed algebra. Because the symmetric operator times the symmetric operator is again a symmetric operator. And so now I want to kind of see what this structure constant depends on, and more precisely what it does not depend on. So, using this equation here, this recoupling condition, you can actually see that if you take, let's say, the product of a Hamiltonian term like this, where this is some Gi, like that, times a Hamiltonian term like this, where this is some Gi plus 1. So I'm looking at this situation here, right? I have some Hi times some Hi plus 1. Graphically, what this thing looks like is this. I can transform this using some of my F symbols, the F symbols of this fusion category D, to a diagram that will look like this. Let me write it like this. And okay, now there will be some more complicated thing. The thing here, G, I don't know, Gi, I plus 1, something like this, right? The point is that the only thing that I need to do to transform a diagram of this form into a diagram of this form is do some of these F moves, right? So what this means is that this structure constant here, this F of x, y, z, is really a function of f of x, y, z, of this F symbol of this fusion category D. But importantly, what it does not depend on is the specific choice of these tensors here, namely the specific choice of module category. So what I'm trying to say here, maybe in a slightly roundabout way, is that if I take such a Hamiltonian, I haven't really specified a choice of module category there, right? But what I'm telling you here is that if I'm looking at the algebra of these symmetric operators, this algebra is completely fixed by this fusion category D. It does not depend on which choice of module category I use to actually define what this tensor looks like explicitly. So independent of this choice of module category over this fusion category D, I'm getting the same algebra of operators, right? Now, the Hamiltonians that I will get if I do this, they will look very, very different in general, but the algebra that they generate will be the same. That's kind of the point. And so, from this, it follows that, well, basically, if you know the algebra of these operators, that's enough to fix the spectrum of this Hamiltonian up to the generices. So you only need to know how your local terms and the Hamiltonian multiply together in some basis to figure out what the spectrum is of that Hamiltonian. One way to think about this is that you could say, I take this algebra as a representation of itself and I just compute the eigenvalues in that basis. And the only thing you ever need to compute this matrix product on the algebra itself is basically the structure constants of this algebra. So you can deduce the spectrum, and it will only depend on these structure constants. So knowing this is enough to determine the spectrum of the Hamiltonian. The spectrum is some algebraic property. So let me write that down. So the spectrum, which I'm going to denote as lambda of h, is a function of course, it's going to depend on these coupling constants, right? So of this set of gi. And it's going to depend on the f symbols of this fusion category. But importantly, it will not depend on any other data that goes into defining these things. So, yes?
Is G a rank 4 tensor on the right hand side?
Yes.
So it's a different set of G's?
Yes.
What are its indices, IJ?
Sorry?
Like what are the indices of G and
GI, I just wanted, it doesn't really matter. I just label it by something that makes sense.
You mentioned the Bx forms an orthonormal basis for
Yeah.
L. So you have a what's it called? Error.
Yes, so the orthonormal basis for this set of matrices, this algebra are basically, so the B are basically of this form. They are diagram that looks like this. And then the norm I'm using to define whether they are orthonormal or not is just taking the trace. So these are orthonormal with respect to just the trace norm on these. Okay, let me push this up. So, explicitly, what I've told you amounts to the following. If I take some Hamiltonian, let's say it depends on some choice of fusion category, choice of coupling constants G, and of course, explicitly, it's going to depend on a choice of module category because those tensors, they depend on this choice of module category through this little triangle F at the top right there. Explicitly, this is going to be some sum of terms that look like this. A little gi here. This is going to be some R1, R2, R3, R4. There's some direct sum of these objects here, just like before, and then Y1, Y2, Y3, Y4, Y5. But those are sort of determined by this thing. So this is one choice of Hamiltonian, local term of Hamiltonian. And then I'm saying, okay, let me now take the same data, H of D, Gi, and this R. Okay, this is just going to be the same picture, but replacing everything with tilde. So the GI, they don't change. One, four. These are two Hamiltonians that if you work them out explicitly using the explicit modular associators, they might look very different. Right? They can act on a different looking Hilbert space. They will have different symmetries, because what I've told you is that the C here, which is the symmetries, they depend on the choice of R. Right? So the only thing I'm keeping fixed is this guy here, because this determines my algebra of operators. The F symbol of this guy determines the algebra of operators. But I'm changing this, and I've told you that these two together fix what this is, if I want this to be invertible. So these Hamiltonians, they will have different symmetries even. Nevertheless, they will have the same spectrum. Because the spectrum is a property that only depends on the F symbols of this fusion category D. And I'm keeping that fixed, I'm not changing that. Right? So these two Hamiltonians have the same spectrum up to degeneracy. That's something that you cannot fix the degeneracy using this kind of argument. But every eigenvalue that appears in this Hamiltonian has to appear in this Hamiltonian, and vice versa. That's what follows from this kind of argument. So, if I think about drawing this in terms of my domain walls.
So what's the statement that you include degeneracy as well? Is there some?
You can make this very, very precise. You can actually write down the unitary transformations that relate these guys. You will have different symmetries here. So based on those symmetries, you can look at the irreducible representation. So your Hilbert space will split into irreducible representations of those symmetries. We're allowing insertion of non-trivial boundary conditions. So really what you're looking at are different possible twisted sectors and all those kind of things. At the end of the day, it turns out that these different sectors are labeled by the Dunfeld center. So your different topological sectors, which is just a way of saying how does my Hilbert space split into ERs of the symmetry, are labeled by the center. And then there's this bimodular category gives you a specific Morita equivalence between the two centers of these two symmetry categories. And the claim is that every topological sector that appears in one appears in another, but its representation on that specific Hilbert space might be of different dimension. That's the precise statement about degeneracy. So one topological sector might appear once in one model and 3 times in another model. That's something that can happen, and then you will get a mismatch in degeneracy. But every topological sector that appears somewhere has to appear somewhere else. Now you have to include boundary conditions for that. A topological sector that appears in one model on periodic boundary conditions might not be there in another model on periodic boundary conditions. We'll have to include twisted boundary conditions. Okay. So if I draw what's happening here in terms of a picture, D. So I'm fixing this fusion category D. I'm saying, okay, let me define 2 different R. So I have this R here and then R tilde. From what I've told you, this fixes a symmetry C and a symmetry C tilde, which might be different, right? They need not be the same. And now, because these are domain walls, I can compose these domain walls and end up with a domain wall between this guy and this guy as well. So, if this guy is labeled by and D of R, and this guy is labeled by and D of R tilde, then it's going to be a domain wall in between these guys, which I'm going to be calling, I don't really want to give it a name, but you can denote it as category of module functors from R to R tilde. So this is something that you can explicitly compute. It's basically the composition of this domain wall with this domain wall. So there is an explicit operator, sorry, there is a domain wall between this symmetry and this other symmetry, right, which you can just obtain by composing these domain walls. This is something that you can explicitly compute. So what this gives you, is an explicit operator that takes you between these two Hamiltonians. So this thing here, G, this thing here, G. There will be some operator, which again you can compute by composing these domain models, that will take you from this situation R1, R2, R3, R4, sum, I'm going to write the sum, R1 tilde, R2 tilde, R3 tilde, R1, R2 tilde, R4 tilde, R1, R2. This thing is labeled by X. And this X is an element of this category fun D from R to R. So again, either you know what these module functors are, in which case that's great. If you don't, you can literally take this as a definition actually. So you can take this as a definition. Module functors are the matrix product operators that will take you from one Hamiltonian to another Hamiltonian. You don't have to guess these things. There are tools to compute explicitly what these things are. I'm using some tube algebra techniques. So there is a operator that we call a duality operator that will take you from one Hamiltonian with some spectrum to another Hamiltonian that may look completely different but will have the same spectrum. That's kind of what we call a duality in physics. Simple examples of this are things like Kramers-Wannier duality between the low and high temperature phase of, or the symmetry and the symmetry breaking phase of a quantum Ising model, but there are many, many more examples that you can come up with this. This is something that's systematic. So if I give you some Hamiltonian with some symmetry, I can write it in this language, and I'm writing down all its possible dual models, so i.e. all its possible equivalent Hamiltonians with the same spectrum that can look very, very different, can just systematically be obtained by changing this choice of module category over this fusion category. Yes?
But there are also, like you had on the other blackboard, you had realized D and C as the module endofactors with respect to the other.
Yeah.
But there should be also like bi-module endofactors, like the ones that are compatible with C and with D. My question would be, what is the role of those for the Hamiltonian? Is this like some kind of common sub-Hamiltonian, or how does it?
Yeah, I'm not sure. I'm not sure about that. Yeah. I would have to think a bit more about this.
Because it's in some sense a bit canonical, so it should be either trivial or in this setting, or it should have some meaning. Right?
Yeah. I'm not familiar enough with with these CD bimodule, with these bimodule. Is it true that you can understand those just by sort of as module functors over C box times D reversed? Is that the same? Sort of put this to the other side.
Yes,
and
this
then,
is a different way of looking at them.
I'm not sure. I think those things probably become relevant if you're starting to impose that you want these two Hamiltonians to be the same somehow, and then maybe if you want this to be like a self-duality or something, maybe that's where it shows up. But okay, I'm not sure enough.
Maybe we can discuss later.
Yeah, yeah. Yes?
This earlier example where D was that B,
Yes?
can you get two different R's this way? Or is that
So, okay, indeed, good question. So, if I take this D to be rep G, if I take D rep G, the different R are given by representation H. So, H. So for these rep G, the different module categories are given by the categories of psi projective representations of some subgroup H of G. So that's all the possibilities that you can get. So this H is a subgroup of G, and then this psi is a 2 cocycle of this subgroup. So if I give you something like rep Z2, there's going to be two options. There's going to be this vec, which is obtained by taking the trivial group here, then you get a category with just one element. Or any fusion category is a modulo category of itself. That's the only option for rep Z2. But if I take something a bit less trivial, like Z2 times Z2, I take a rep Z2 times Z2, you will find 6 different modulo categories. There's going to be 5 different subgroups, and then for one of these subgroups, which is the group itself, there's going to be a projective representation. So that's going to give you 6 different modulo categories. So if you give me a Hamiltonian with a Z2 times Z2 symmetry, I will be able to generate 5 other Hamiltonians from this construction, which have exactly the same spectrum. That's the sense in which you should think about these things. All of these models, well, some of these models will have distinct symmetries, right? So some of them will have, if you take something like Z2 times Z2, well, no, I think actually in that particular case you only end up with Z2 times Z2 symmetry. But if you take something like a model with an S3 symmetry, in which case this category D would be rep S3, some of those Hamiltonians would have non-invertible symmetries. Some of them would, if you take this thing to be, if you take R to be rep S3 as well, then this symmetry is going to be rep S3 as well. That's a non-invertible symmetry. So you can get dualities between Hamiltonians with just normal on-site symmetries, something like the Heisenberg model, to a model with non-invertible symmetries. And they are dual, they have the same spectrum. That's something that we actually use in the last bit of the lecture. Yes?
By choosing different R and R prime, you get a different Hamiltonian.
Yes.
But this X map the operator in one Hamiltonian to the other.
Yes.
But X in general is not inverted.
Yes, indeed.
So it is not a symmetry.
It becomes
or
so you can use these X's to build unitary transformations, but you have to include directional boundary conditions. If you're careful with boundary conditions, you can turn these things into unitary operators. But you have to be very careful with how this thing acts on the boundary conditions.
So you mean it has nothing to do with the fact that in general X is not equivalent?
No. So for a general, I mean, the way you have to think about this is basically the level of cube algebras. You have some cube algebra that describes the topological sector of one model.
Yeah.
You have a cube algebra that describes the topological sector of another model. And then this thing basically acts as an off-diagonal block in the cube algebra. You can go to a basis where these things then act as a unitary. With the caveat, of course, that you have to, or an isometry, I should say, with the caveat, of course, that you have to include the action of on-boundary conditions. So we have a paper where we, well, where we one, write this explicitly as a unitary transformation, and two, explicitly write it as a quantum circuit as well. So a generic operator like this, you can write in terms of a linear depth quantum circuit, and something that we did.
When it indeed can realize in the unitary setting, then what is the inverse of the unitary? Does it come from
You have to be careful.
a factor from the other way, or?
Yeah, I'm not sure how to explain it in words that you're familiar with, but I can draw some pictures in terms of cube algebras, and it will be clear what it's supposed to do. It's not very clear. Okay.
And this Hamiltonian picture, the R's, are they summed over, or is it like a fixed choice?
Yeah, no, they are summed over. I have to sum over them, otherwise that equation breaks.
Okay.
So to get this equation here, I have to sum over the loop that's sitting here. So I have to sum over.
Oh, I see. So then the sum over the two elements already implicit also.
Yeah. So indeed, I haven't been very careful here, but if I want this equation to hold, there needs to be a sum over this R4 here. Here it needs to be a sum over this R4 tilde. This sum is the sum that appears in the Pentagon equation. That's why this is just some Pentagon equation.
Four R's there. So we have to.
Yeah, so it's true for any of these outside labels, but this inside guy here is summed over. But then when I'm defining the Hamiltonian, I'm defining my Hamiltonian as, well, as like a direct sum over all these R. I cannot fix these R's in the Hamiltonian, because if I fix it, then I can't sum over it when I'm hitting it with the symmetry. So it has to sum over all these values, otherwise it breaks the symmetry. I don't have to sum over these white ones. So this equation at the top left there is true for any of these white guys. So these guys are the y1, y2, y3. I can fix this to be whatever I want. It will still commute. Okay. Let me say something. Yeah, sure.
So for C2, C2, is one of the dualities you get the same as the is it the same as the Kennedy-Tzolk'li transformation? So yes, yes,
yes, yes. So for if you take rep Z2 times Z2, there's a FEC as a module category, which is just rep of the trivial group. There's a duality to rep psi of Z2 times Z2. And this is something that's known, it's called the Kennedy-Tzolk'li transformation. It's a thing that was written down in the 80s already, a long time ago, without really having any systematic framework behind it. This sort of guessed that there was a kind of duality transformation between these two models. This framework generalizes these kinds of dualities to any possible symmetry that you want. So this is like a completely general, systematic recipe for generating dual Hamiltonians given some Hamiltonians. Which, okay, dualities have been useful in the past to determine things like critical models and to explore phase diagrams. But in sort of the final half hour of this lecture, I'm going to convince you that these things also are extremely useful numerically to kind of actually find matrix product state ground states using variational algorithm. Okay. I want to draw one kind of quick set of pictures to relate these duality transformations to something that we've talked about before, namely gauging. So Niels talked about this when he was talking about defect TQFTs. There is a connection between these special symmetric Frobenius algebras and these duality operators. So I did this all for Hamiltonians because it's easier to talk about the algebra of operators in that case. But I can do exactly the same thing for some Euclidean path integral model, right? So if I want to write down some partition function with some symmetries, it would also be built from these kinds of tensors, and I would have these symmetries that can move freely through it. And you can also define dualities for these partition functions. So,
excuse me.
Yes?
Kind of all the case now.
Yeah, it's just more subgroups, and I don't know what the second cohomology is of Z2 times Z2 times Z2. It's more complicated, I'm presuming, than... I don't know how many there are, but it's something that you can compute. So you just have to check all possible subgroups of Z2 cubed, and then look at all the possible second cohomologies, so you're just going to get a whole bunch of dualities and transformations between them. One can compute this. I don't know it off the top of my head.
So here you have just H2, second form, there is nothing about H3.
No. So let's imagine that we have some partition function written in terms of these tensors. So I have this bulk theory, and let me put it on torus. So this is the torus partition function of some model with some MPO symmetry. So there's these symmetry lines here that I have to draw. I can freely move throughout this thing however I want. I'll erase this again because I don't want them. But this partition function explicitly depends on exactly the same as this Hamiltonian. It depends on this fusion category, it depends on some couplings, but crucially it depends on this choice of module category here. So this choice of module category is the only thing I'm going to draw explicitly here. So let me check that I don't mess it up. So let me say I have this partition function here on the one hand, and I have this partition function here where I keep everything the same except for this R. So I go to this R tilde. And I ask, what is the relation between these partition functions? How can I relate these guys? Well, what you can do is you can take this guy here, the one with R tilde, And you can insert a little bubble, sort of a little domain wall, where inside this bubble, instead of R tilde, I have this R. So this bubble is going to be labeled by this module functor here, because this module functor is exactly the thing that's taking me from R to R tilde. I'm putting in a little bubble, and I'm telling you that this little bubble, okay, can shrink it until it disappears, right? So this thing is really, at worst, proportional to this. In the best case, this is just identical to this thing. And now I can start to manipulate this little bubble by growing it around the torus. So this is going to be equal to this. Let's see, R, and then here in the middle I still get R tilde. This is all labeled by X. X. And now I can fuse this little bubble with itself to get something of this form. I get something that. And this is now R. And these red lines, they are obtained as the product of X with X tilde. So this is going to be a symmetry of this R here, because it's clear that I can move this wherever I want, right? So this has to be some object in the fusion category C, which are the symmetries of this guy. But it's going to be a very particular object. I'm going to label it by A. So this A, explicitly, I write it in white. So this A is something called the internal home in, say, C, I think. I forgot exactly what the notation is. X with itself. So this, okay, it doesn't really matter what this is if you don't know what it is. What's important is that this kind of way of constructing an object in the fusion category C gives you a special symmetric Frobenius algebra. So this A here is a special symmetric Frobenius algebra. And you can easily check. You can easily check that all the axioms for a special symmetric Frobenius algebra are satisfied if you define this object basically as the composition of this X with itself. And this is what Niels talked about when he talked about this orbifolding or this defect EQFT. So what I've shown you is that if you take this theory here and you replace this module category by this R tilde, this is basically equivalent to taking the original theory and inserting this set of topological defects here. Now these Frobenius algebras, they are such that you can freely recouple them without anything, so they're kind of special in the sense that this is all still very topological. This is called an orbifold, or in more modern parlance, this is called gauging. So what I'm doing when I'm changing from one module category R to some module category R tilde is really I'm gauging by some algebra object A, some special symmetric Frobenius algebra object A. So these changing the two of one module category to another module category, really what it amounts to is gauging of some symmetry. Now, this kind of construction, doing this at the level of the Hamiltonian, is in general a little bit complicated. You can do it, but to be honest, it kind of sucks if you want to do it explicitly. This is much more explicit and much more straightforward. You can actually prove that these two approaches are completely equivalent, but it takes some work. This is kind of immediate. Given one Hamiltonian, I just have to compute some module-associated data to find the dual Hamiltonian, and that's it, I'm done. If you try to do this gauging explicitly, it's a little bit complicated. So this is kind of a shortcut to doing this gauging, but it is completely equivalent.
Can I?
Yes.
Just one comment?
Yes.
So
I probably messed up some notation there.
No, it's all good. I wanted to say when you said earlier that even, I mean, this X doesn't have to be invertible, right? So that's the point you made.
Yeah.
And then it's sort of from this point of view surprising that it can give a unitary.
Yeah.
But you see that over there, you see the comment that we have to be careful with the boundary conditions, because you do get an X equality of partition functions, even though the X is not invertible. But as the output side, you do have all these twisted sectors given by A. And so these are the extra boundary conditions you have to take into account.
Yeah, exactly. That's a very good point. So you can make this a bit explicit at the level of the Hamiltonian as well. let's say that I have some Hamiltonian here and the dual Hamiltonian H tilde. And I ask, what is the actual unitary, how do I get a unitary transformation between this Hamiltonian and this guy? What you can do is draw this kind of picture here. So let's assume that I'm on periodic boundary conditions here. This is labeled by x. This here is h, and this is going to be, well, h tilde, this is going to be the dual. I can fuse these things together like this, and end up with this algebra object here. And now, this thing here is basically unitary transformation, because, okay, if you're lucky, and we are because we're working with unitary fusion categories, this is going to be a unitary matrix product operator because this thing is its dagger. And together they disappear because together they just form this little bubble that I can shrink to nothing. So that's the sense in which this is unitary transformation. It's only unitary if I take this theory and transform it to this dual theory, but I have to insert these boundary conditions. And that's the point you were making in the Euclidean case. We can make this explicit in the Hamiltonian case as well. Thanks for that. Okay, any other questions before I move on to the final bits of this lecture?
There's an extremely primitive question, sorry, but you have, just keeping track of the right object, you have two fusion categories here, C and D. Right?
Yeah.
Do I understand correctly that you're using one of them to build the Hamiltonian and the other to be closest?
Exactly. Yeah, and for these things to be consistent, they have to be connected by an invertible bimodule.
So that's always the picture that you
Exactly, yeah. So, because one of them encodes the Hamiltonian, more precisely it encodes the algebra of operators that enter into the Hamiltonian.
Sure.
The spectrum is an algebraic property, and so by keeping this fixed, I can change this Hamiltonian without changing its spectrum. That's what I'm doing by doing these things. But indeed, explicitly, you can come up with these. You can build these unitary transformations explicitly in this kind of, in this way.
Could I ask about that point over there? When you said changing from one bimodal category to another bimodal category.
Yes.
Gauging.
Yeah.
What is the gauging, the HIJ or the
so normally people, well, there's a way to gauge fusion category symmetries by saying I take some Frobenius algebra object, special symmetric Frobenius algebra inside that fusion category, and then I make like a superposition of all possible topological defect lines in that partition fiction. That's the modern way of thinking about gauging. It coincides with the usual notion of gauging that we have in terms of taking a global symmetry and making it local. You can make that very explicit, but this is kind of the modern way in which people talk about gauging.
But the Frobenius algebra data, is it the same as this Morbifold data?
Yeah, it's the same. Right. Any more questions? Yes?
Why do you call A an algebra here?
It's an algebra because it satisfies these rules. So this algebra object is such that this is equal to this on the nodes. There's no associated there anymore. There's a multiplication map on this algebra, which is basically this vertex here. It's not a vector space anymore, it's just some vertex. And it satisfies this property. So this is an associative algebra. This is the associativity condition for the algebra. So this algebra object inside a fusion category is a collection of objects and a choice of multiplication of those objects such that it basically cancels out the F symbol that you would normally get. So normally if you draw an equation like this in a fusion category, there would be an F symbol here. But this algebra object is chosen in such a way, it's a particular subset of the objects and a choice of multiplication such that they sort of eat up this F symbol that should be here. That's why it's an algebra. Does that help, or? Oh, yeah, indeed. Okay, good. So, for a given bimodule category, there will be many different x's in this category of module functors here that you could choose. The point is that if you construct the algebra from these x's, these algebras, they might be different for a given x, but they will all be Morita equivalent in some sense. So there will be some equivalence between these algebras. They are one Morita equivalent as algebras. They have the same representation. So indeed, you can choose whichever x you like here. you will end up with an algebra. Sometimes that algebra will be different, but there's an equivalence between the algebras that you obtain in this way. Does that help? Or?
Yeah, I'm having trouble establishing which level to think about these things.
Okay, but I can give an example if there's some time at the end, or maybe just after, or later this afternoon, of an explicit example. But for instance, do you know the Fibonacci fusion category? Is that something that you're familiar with? Okay, well, I was going to give an example there, but let me.
Oh, sorry. Also, I just got confused by what you were saying. So X is an element of C, right? Because
No, X. Sorry, here X is. Yeah, I'm using this red color to denote both this guy, but also this guy here. So here, this X is.
Oh, it's R
this
to R
duality.
tilde. I see. Okay.
It's the module functor from R to R tilde. I'm also using red because, well, I'm running out of colors to be honest, and it's just too big of a mess.
But then when you wrote A equals hom, I couldn't quite see. So this is going from.
This is called the internal hom. So it's something that's defined by.
Ah, okay. You're assuming there is an internal hom, I guess.
Yeah.
And so it's going from X to X. Is that what you said?
Yes.
Oh, okay.
Yeah. So it's basically you take X to. There's some nice way to define this, but I don't want to.
Yeah, that's.
Okay, good. What do I want to keep? I will push this up. The final thing I want to talk about is phases for models with matrix product operator symmetries. Just like in the first lecture I talked about, if you have a model with some finite group symmetry, you can use the theory of matrix product states to basically figure out that there's some non-trivial classification there of phases. Symmetry protected topological order, which we saw was classified by second cohomology, and I told you that if you have one matrix product state that transforms according to one element of the cohomology class, and you have another matrix product state that transforms according to another element in this cohomology class, that you cannot connect them with a constant G-symmetric circuit or a sublinear depth G-symmetric circuit. So that's what we take to mean as these things being in a different phase. So now I want to repeat this classification but for these more general matrix product operator symmetries, because it's something that you can do explicitly. And so, I forgot what number we're at, but okay, whatever. Matrix product operator symmetric matrix product states. So let's assume that I have some OX acting on some state where I'm going to allow this state, I'm going to allow symmetry breaking as well. So I'm going to allow my symmetry to actually take one ground state to another ground state. So I have to come up with some labeling for these different ground states. Let me call this labeling M. I'm going to say, okay, this is going to give me some sum over M2 of some number, X, M1, M2, times psi of M2. So I have some state here, I have some matrix product operator acting on this state, and I'm telling you, if I act on it, I get some linear combination of states that again will be ground states, because this is a symmetry of the Hamiltonian, right? So this is going to be a ground state. Now, again, this is something that we're going to impose for any number of system sites, so any number of sites, in which case these things have to be integer again. It's exactly the same argument that we kind of used before. Now, if you assume that these things are matrix product states, which for ground states of a local gap Hamiltonian, you can assume this. This equation, using this fundamental theorem that we talked about before, allows you to find a local condition that will make this thing true. So explicitly what it looks like is I will have some tensor A here, which is my matrix product state. I will have some, okay, let me draw it like this. Some matrix product operator that acts on this. And then the fact that it is invariant under this, or exactly more precisely, the fact that it transforms in this particular way, will imply the existence of a tensor like this, which, let me call it, I don't know, F. No, well, F, yeah, fusion tensor, doesn't really matter. That implements this condition at the level of this local tensor. F. So I'm assuming here that this psi is a state generated by this MPS tensor A. Now this A, of course, has to depend on this label, so there's going to be a label M1 here, a label M2, and this red line is labeled by X, X. Actually, I can actually sort of copy over this label to this line here, so it's going to be 1, 2, 1, and 2. So I'm just using the same kind of logic that I used before when I was talking about products of matrix of operators to say that exists some kind of tensor that implements this product at the level of these local tensors. I'm just doing exactly the same thing here, but now the only difference is that one of these things is not an operator, it's a state. But it's exactly the same argument. Now, from this, you can deduce that, let me write it below. You can see that this kind of thing has to satisfy a consistency condition, namely that this F let me see this like this. So this is x1, x2, m1, 3. M1, M3 is equal to connect the lines properly. This. So x1, x2, m1, m2. So again, these M1, M2, M3, they're labeling the different ground states. X1, X2, they're labeling the different symmetry operators. This has to be equal to this up to some number, which we're going to call this triangle F again, because that's what it's going to be, of well, X1, X2, M1, M3, and X3, M2, and then okay, there's going to be additional indices here because these tensors here, for every, there's an additional index I here, where this I runs from 1 to n of x m1, m2. So for every possible way of going from m1 to m2, you get one of these tensors, so there's an additional index here. And if I put these indices here, I, j, k, l, these become these extra indices here. So I again have some 10 index f symbol that's describing the associativity of this thing up to some number. This is a module associator, so for this whole thing to be consistent, this has to satisfy a pentagon equation. And so what I've basically derived here is that phases of, so gapped phases for a fusion category symmetric Hamiltonian are labeled by module categories over that fusion category. And just like before, that you can prove that these matrix product states, if they are in a different SPT phase, you cannot connect them via a finite depth quantum circuit. You can prove that matrix product states labeled by a different module category cannot be connected with a finite depth circuit. So this is just a generalization of the statement that we had about SPTs to this more general case. You can prove that if you have two matrix product states that transform according to this same module associator, or at least one that's equivalent to it, that there is an adiabatic path of Hamiltonians that takes one to the other without closing a gap. So these things, this is really like a proper invariant of the phase. If it's the same, two things can be connected. If it's different, then you cannot connect those two things while preserving the symmetry, of course, without closing a gap. So this is the classification of phases just for these general C-symmetric Hamiltonians.
Sure, I understand. So here the X is an object in the fusion category.
Yes.
And the first on the left-hand side of the bottom line is the F symbol from the.
This is the fusion tensor that we got just from before, exactly. So I should have written it different, but okay, I'm running out of notation. Okay. So with this in hand, finally have all the ingredients to make my kind of the points that I wanted to make in these lectures. Let me put here phases of a C-symmetric Hamiltonian are labeled by module categories, which I'm going to call P. Module categories P over C. So P for phase, right? Before we had a module category R, and there was the R for representation. So very, very deep thought going on here. And now I want to make a diagram that kind of summarizes all these things. So I've told you that a matrix product operator symmetry is described by a CD bimodule category, right? That's what we talked about last lecture and that we've been talking about today. And that's, okay, the duality amounts to keeping this fixed, but changing this. In that way I will generate Hamiltonians with the same spectrum that I can operate. So what I've also derived now is that phases of matter for a C-symmetric Hamiltonian are labeled by choices of module category over C. So I can put this P here. Oh, sorry. This denotes that P is a module category over this C here. Now you might wonder what is living on the other side. I told you that if I require this to be an invertible bimodule category, there has to be something sitting here. I will label this something sitting here by E, and I'm not going to derive it, but those turn out to be the excitations, the elementary excitations in that phase. So to give you an idea, if you are in the symmetry breaking phase, so let's say you have a normal group symmetric model, you're in the symmetry breaking phase, your elementary excitations will be domain walls, so basically places where your two different ground states meet. There will be some energy penalty. And your excitations will be labeled by group elements themselves, right? They're basically obtained by acting with the group operator on half your system. So your elementary excitations, or at least the topological aspects of your elementary excitations, are labeled by the group elements themselves. If you're in the symmetric phase, then you know that excitations are labeled by charges of the symmetry, so representations of the symmetry, right? So if you're in the symmetric phase, your elementary excitations, they are local excitations, they are not domain walls, and they transform according to some representation of the group. And then there's all the situations in between. What if I have some partial symmetry breaking? Then your excitations will be labeled by something, which in general can get kind of complicated. This is kind of captured by this formalism. So the example I gave before would amount to saying I fix this to be vec G, so just saying I have a group symmetry, and then this P here would be labeling the different ways in which that symmetry can be broken or in which it can be implemented projectively. And for all those different choices, I would be able to tell you what this E is. And this sort of invertible bimodule construction gives you a way to predict, or basically to write down what this E is given some phase. So this is an invertible domain wall, and this is an invertible domain wall. It's very natural to try and connect these two things together by another invertible domain wall that's just obtained by composing these guys. So,
excuse me, is
yes.
P in this triangle the same as the P in the little box on the left?
Yes. Yep. So
it is invertible.
Yes. Yep. So in this little box on the left, the only thing I talk about is this bit C and this module category P. But now I'm telling you, okay, anytime I have this, I can extend this into an invertible bimodule category uniquely. This guy is going to be fixed by basically C module and the filter from P2 itself, right? So that's something that's fixed, I can compute what this thing is. And okay, you can show, and I'm not going to do it here, I'm happy to do it later, but that these will label the elementary excitations in that phase.
So until just now, I thought that the rough picture of what you're explaining is that you have the lattice model with your Hamiltonian on one side,
Yeah.
and then there's the symmetry in the bulk described by the category C.
Yes.
And then it has a boundary condition, I thought, called P.
Yeah.
And the whole thing is the sandwich.
Sure.
But is it if P is invertible? Or if it
No,
can be made
it's like if you take a 11-1 model and you have a boundary condition labeled by P, there will be boundary excitations, right? And those will be labeled by the end of functors from P to itself, C module end of functors from P to itself. That's what I'm talking about, these boundary excitations. That makes sense?
But the sandwich picture I outlined is correct?
Yes.
And couldn't there be more than one isomorphism or equivalence between the crushed sandwich and the theory that you actually want to study? Do you have a choice there?
Well, there's some choices being made here, right? So I'm choosing to represent this Hamiltonian in a particular way. So do you have the SimTFT picture in mind? Is that the kind of thing that you're thinking about, or?
The sandwich picture?
Yes. Yeah. So this would describe both topological order. This would describe one choice of boundary condition. And then there will be another choice of boundary condition, which is actually going to be the thing that's sitting here. And those sandwiched together will give you this guy. That's the way it fits in this language. Okay, we can talk about it later in detail. I was sort of about to finish this argument. So I have this bimodule category here, which basically describes the Hamiltonian, right? Well, let me say, this thing describes the Hamiltonian. This thing defines the representation of the Hamiltonian. So when I say Hamiltonian here, I mean some abstract algebra of operators. Here, this determines some representation of that abstract algebra of operators. This determines the symmetry. This thing determines the phase. This thing determines the excitations. So it's very natural to wonder, okay, what do I get if I compose these things together? Okay, I have P and then R, so let me call this Q. And the question is, what does this mean? What is this thing? Is it any useful? Now, I've also talked about duality, namely that duality amounts to keeping this constant and changing this, which will of course also change your symmetry. So let's say that we now do a particular duality to this case, where we pick this R to be equal to this Q. So now I'm just sort of playing some games with composing dummy walls. So let me say I take this R to be equal to this Q, in which case I'm going to get E here as well, because now it's the same. But in particular, what I will find is that my phase is now labeled by the same module category, by the same fusion category that labels my symmetries and that labels my excitations. So what I've done here is I've kept this fixed, I've changed this into Q, and it just turns out that if you compose this one with this one, this is basically its inverse, you end up with the trivial invertible bimodule category. So E as a bimodule category over itself. And you might think, okay, that's great. It's something that you can always do. This is generic for any representation of the Hamiltonian. In any phase, you can always do this. Now you might wonder, why is this useful? Well, this thing here, this implies symmetry breaking. And why is that useful? What I've told you here basically is that for any Hamiltonian in some phase, there is a duality I can do to a dual Hamiltonian, a different Hamiltonian, that will be in the symmetry breaking phase. Now, being in the symmetry breaking phase is very, very useful, because imagine that you're trying to optimize some matrix product state for the ground state in some phase. If it is in a non-trivial phase, if I have a condition like this, that means that this matrix product state is not generic. If I just parameterize this in terms of some variational parameters, those variational parameters cannot all be independent. There must be some constraints there, because it has to satisfy this equation. The only case in which your variational parameters are truly unconstrained is if you are in the symmetry breaking phase. In that case, all your variational parameters are independent, because the action of the symmetry operators on one ground state, it just takes you to a completely different ground state, and there's no relation between these parameters anymore. So what I'm telling you is that if you want to simulate a model, try to find a matrix product state, ground state, for some model in some phase, it's better, it's more efficient to go to a dual model where you are in the symmetry breaking phase. What I've told you here basically proves that you can always do this. And because these models are dual, you can basically compute any correlation function that you want in one model, you can just compute in the dual model and then map it back. It doesn't matter. So the final point that I want to make, the final picture that I want to draw is that, let's say that I have, okay, the point that I want to make is that a generic matrix product state in some phase is obtained by taking this duality operator, this module vector, where this guy is labeled by R here, that's my original Hamiltonian. And here on the bottom I get these Q, and then I act on some generic matrix product state like this. And then this red line here is labeled by P. That's the duality operator. So any matrix product state in some phase P can be written like this. And so this kind of gives you an explanation of what this Q is. This Q here, it's the entanglement degrees of freedom of a matrix product state in this particular representation of the Hamiltonian in this particular phase. So that's kind of the message I want to go to in the end, is that using these tools, you get a way of parameterizing matrix product states in a generic phase in such a way that there's no more redundancy. So all the fact that this state is in some phase is taken care of by this thing, and then you just have to optimize these variational parameters, which are completely unconstrained. So that's where you get a sort of computational advantage, is that you're not spending time optimizing over parameters that are actually related because you're in some phase. No, it's completely unconstrained. And so you gain in memory, you gain in computational time. And so this is kind of a way to, well, we kind of took a very big detour. We started with these variational tensor network methods, said that they were useful, and took a very big detour to studying the representation theory of this matrix product operators, duality transformations, and in the end we arrived back at this kind of picture where we can use all of these ideas to just make better code. This is something that we recently implemented, and it works well, and this is now the state of the art for exploiting these symmetries in tensor network methods. So that's everything I wanted to say. Thanks very much.
Thank you. Do we have questions?
I have two questions.
Yes.
The first one is, could you draw another final picture, which is the sandwich in the situation?
I have to think a bit how it would look like. I'm not sure how to draw the state. So I'm pretty sure it's something like this, where you have... okay, I never draw these pictures, so I'm horrible at actually drawing cubes. Like this, right? What am I doing? Like this. Sorry. Yes. So in the bulk you have Z of D. Right? It's some topological model in the bulk that's described by the center. You mix. Sorry?
Okay.
I'm labeling by Z of D. I can label it by D of L, but okay. It's something in which you have topological operators that are labeled by Z of D. One of these boundaries is going to be R, which is what people call the symmetry boundary. Another boundary of this is going to be this Q. And if you take this sandwich, you end up with something that's labeled by P.
Oh, and the construction of Q is part of the mystery because you didn't have time to explain exactly how to construct NQ?
Right. I mean, if what I explained was this bit and this bit. What you can infer from this is the existence of something like this, and I just gave you the interpretation of what this thing is, but it means the excitations of this thing. I can compose this now to arrive at this Q. And then using these kinds of arguments, I gave an interpretation of what this Q is. So these Q are the entanglement degrees of freedom that I have in this thing. I'm not too sure how to think about it properly in this language. I think this is just saying that if you're writing down some states for this particular given symmetry boundary condition, and you want to end up in some particular phase P, you have to choose this Q appropriately. That's kind of, I think, the way of thinking about it. But I'm not very well versed in this language. I just do tensor networks. But these things are sort of one-to-one related.
If I may ask my second question.
Yes, sure.
So towards the end, you briefly said what the state of the art in terms of computability is.
Yeah.
That went over my head.
Sure.
So in the first lecture, you explained that the tensor networks, one of the key properties of the tensor networks are that you have way less parameters and it doesn't grow exponentially.
Yeah.
Is it roughly true that if one wants to add domain walls and defects and so on, and does this in the setting where you started from the nice tensor networks, which were more efficient, then things stay more efficient, and that's why this is successful? Or do these module by-categories and so on make it even more efficient?
They make it even more efficient, but not so no longer by, so just by using tensor networks you get this exponential compression, and then by using these things you get some factors. So it's basically you can divide the number of variation parameters by 2 or 3 or 10 or something like that, but it's no longer some exponential reduction. But you gain this kind of, basically this whole sandwich here gives you a matrix product state with a much bigger bond dimension than if you just have to look at this guy. So what you're doing is basically you go to this dual theory, which amounts to pulling your Hamiltonian through this. You find the ground state for that dual theory, and then you map it back using this operator to a ground state of the original model. But this operator also has a non-trivial bond dimension, and if you didn't do it like this, your algorithm would have to figure out what this thing is by itself. Now what we're doing is we're saying, go to a phase where this structure is not present anymore, do your variational computation there, which will require the minimal amount of parameters, and then go back to your original Hamiltonian, and this will increase the bond dimension. You can multiply by a factor of 2, but that's quite costly in practice, right? That's not a non-trivial statement. So you gain something like a factor of 2 in bond dimension, which in terms of memory gives you like a quartic speedup, and then in quadratic speedup, and then in terms of computational time actually gives you a cubic speedup, because these algorithms work by having to diagonalize matrices. And if you can make a matrix twice as small, in terms of computational time is actually 8 times as fast, right? So there's a really like computational gain there, and it's because you're sort of pulling out the structure that you know to be exact because you're in a given phase and letting it optimize there before then manually going back to your original thing. That's the kind of idea. Yeah. Yes.
You talk mostly about MPS and PEPs, right? But there are other tensor networks like Mera.
Right.
You say something about the category structure in other tensor networks.
So you can. So I talked about symmetric tensor networks in some sense. So you can think of a. So for those that don't know, Mera is like a modification of matrix product states in such a way that you can still capture logarithmic area loss. So in a critical system.
The E is entangled, right? The R was normalization.
Multiscale.
Multiscale.
Entanglement, renormalization, ansatz.
Okay.
It's a way to modify your tensor network states in such a way that you can still capture a logarithmic divergence in your entanglement entropy. So basically give it some kind of tree-like structure so that any bipartition gives you a logarithmic amount of edges that goes to this. Mera is very difficult in practice. There's 2 people in the world that can optimize Mera properly, and both of them don't work on Mera anymore. And I think sort of in recent years, matrix product states have sort of, with the development of things like entanglement scaling theory, people have understood that even for gapless systems, because matrix product states just work so well, it's better to use these matrix product states, even if in the case that it's a gapless theory. That being said, you can still use these kinds of pictures. This is basically a theory of symmetric tensors. It doesn't matter whether it's a matrix product state, whether it's a Mera, whether it's a PEPS, whatever. this will still hold. And there are some papers that use these kinds of tensors in Mera, so you can use MPO symmetric Mera and study those kinds of things, and all the things that I said about duality operators here should still be true in that case as well. It's just that they are tuned to gapless phases, and gapless phases are not classified by these module categories, they're classified by something more complicated.
So are you secretly telling us that we should forget all the other tensor network construction and buy MPS?
Okay, let me put it like this. MPS just works so well that even though sometimes it's technically, theoretically not the correct ansatz, it just completely outperforms the actually finely tuned ansatz because it can be optimized over so efficiently. That's my statement. I can tell you a less politically correct version of this. Yes?
I understood like the general philosophy here was to maybe use these special Hamiltonians, which are built from these commuting pieces, to model sort of a larger set of gapped Hamiltonians.
Yeah.
Give it access to the low energy states.
Yep.
Then at the end, you were talking a little bit about excitations and domain walls and so forth.
Right.
Is it clear that in this larger case where the Hamiltonians aren't just built from these commuting pieces, that those low energy excitations are the same ones you find in these special class of Hamiltonians where all the pieces...
Right, okay, so I mixed sort of two things. I was talking about commuting projective Hamiltonians in 2 + 1 dimensions. That was really just tricks to derive this theory for matrix product operator symmetries in 1 + 1 dimensions, right? So I use those exactly solvable models and everything we know about those models to derive these kinds of symmetries. Then I was looking at 1 + 1D. I'm looking at generic Hamiltonians. This Hamiltonian here, it's whatever, right? It's not commuting projector, it's some interacting Hamiltonian, it's the Ising model, it's the Hubbard model, it's whatever you want it to be, right? With some symmetry. And then these tensor network-based methods, they give you a way for computing the ground states, but then there's something called tangent space methods, which allow you to compute excitations on top of those ground states as well. You could do that efficiently as well. And that's something that all fits in this kind of picture. I don't know if that quite answered your question, but I just wanted to make the distinction that in the second lecture we used commuting projector Hamiltonians in 2 + 1D to derive this mathematical structure and to give some intuition as to where it comes from. I could have just given you this 3-line notation, but then you would have been a bit strange. In this lecture we're looking at generic 1 + 1D Hamiltonians, not commuting projectors, they can be whatever you want.
I propose to maybe have the remaining discussion during the coffee break, and we meet again at 11 for the exercise classes of Loutens and Caroline. And now we thank Loutens very much for his nice presentation.